And we're back. Happy Thursday. Today we will continue on with our discussion of the general structure of an operating system. But before we begin, some administrative bits. Of course, the reading by September 3rd is pages 3 through 51 in Operating System Concepts, the main text for the course. Please make sure you're keeping up with the reading. Homework 1 has been posted on the Blackboard this past Tuesday. It is due September 1st, 2020 at the usual 1 second before midnight. That's 11:59 and 59 seconds. So where we last left off, we talked about the computer system organization. And this sort of mimics the human body in that we have a high-speed data substrate, and that high-speed data substrate acts kind of like the spinal cord. It's called the system bus. And the purpose of the system bus is to transfer information from among each or between each of the components that collectively comprise your computer system architecture. And so we have one or more CPUs. That's sort of like the brain that does all the computation. We also have a set of device controllers. We have a disk controller, and that device controller knows how to talk to each one of these devices, all the details about how you control these devices. That's on the device side, so that's the device side. And then on the interface side, or the system side, I'll call it system side, it has a buffer that allows you to send data to this device or get data from that device, in addition to a bunch of control registers that high level allow you to give commands to this controller to enact certain behaviors for these respective devices. So we have our CPU, we have the disk controller, we have a USB controller that might control things like your printer, your mouse, your keyboard. We also have a graphics adapter, which is a kind of controller that controls your monitor. It displays pixels and it updates shapes rendered out to your monitor for you to see. You also have main memory. This is typically random access memory, or RAM, and the CPU, every time it is running instructions, those instructions are actually stored on disk. They're loaded from the disk by the CPU into RAM, and that program sits resident in memory. There's your program. And that program, pieces of it are read across out of RAM onto the CPU across the bus, the instructions for your program for execution. And so you have all of these devices operating concurrently, and they're interacting with one another, trafficking data back and forth between pairs of devices through the system bus. And therefore, whenever you spec out and try to buy a computer system, if you really want high performance systems, what you'll notice is that the bus speed always limits the performance of your system. And so when you work or try to spec out or buy or look up a high performance workstation, what you're really paying for is all that engineering that goes into the bus and the balancing of each one of these devices that are interconnected. And so don't be deceived when you see a spec on a system. You have a fast CPU and a fast disk and a fast printer and all those other things. If the bus is very limited in the amount of bandwidth, the amount of data that it can accommodate, that's going to be the bottleneck, and your system is going to be slower. So you want to make sure when you specify a system that you make sure that the bus bandwidth is sufficient enough for the purposes that you have for the types of applications you're trying to run. So let's take a look at the structure and operations. And so you have a computer system. You have a number of input devices. Perhaps you're using audio, and your microphone is connected to an I/O controller that takes all of those sounds input to the microphone, digitizes it, turns it into a ones and zeros byte representation. And then you might also have other inputs, like maybe you're live streaming a performance, right? So you're using audio and video capture going into your graphics adapter or your capture card, digitizing those audio and video signals and turning it into byte representation. Or maybe you're writing a document, right? You're typing, you're inputting things. It could be with a pen on a tablet, or it could be on a keyboard. So you take these things and then you might have them sent to some output device. So if it's audio, you're going to render these to your audio system, speaker system, and you're going to play some music. You might code it with all sorts of other interesting things to give you so-called 3D sound. Or in your audio, if one sound moves, you can literally code your sound such that the sound actually physically travels from one speaker to the other. So there are very interesting ways of outputting this audio data. The same thing with this audiovisual, these live streaming performances. You could code it with 3D information, so you have on 3D goggles and it looks like you have a 3D immersive experience. It could be on a screen that's very, very high resolution. So all sorts of interesting ways, high def, low def, 3D, and so forth. Or perhaps you might recode this information, and you hear my dog in the background barking. You might recode this information. Maybe you would code it as black and white instead of as color to save space. And when you have documents, you code it. You talk to an I/O controller for your printer, a device controller, and this device controller knows how to move all of the printing elements in your printer and actually render these things out as text, spit out a page, and you have a printed document. And so all of this is executing at the same time concurrently. All of these device controllers and the CPU can execute concurrently. And by operating concurrently, you can actually get a lot more done on your system and make efficient usage of all of the hardware and resources that you have available. So for example, why stop your printer just because you're surfing the web and watching some streaming video? So why is it important that these can execute concurrently? It's beneficial. Absolutely. It's important so you get more done, but it introduces some issues, right? If you have all of these devices operating concurrently, sometimes if they're interacting, some things need to wait for others. So for example, if your CPU is interacting to present you a media stream, maybe you're watching Netflix or some other such video streaming platform, well, you need to get data from your network card from the server on the other end of the internet before you can render it on the graphics card to get to your screen. So if there's not enough video data to actually draw out the next few frames of video on the screen, well, you're going to have to wait. The moment that video data is ready, then it's time to go ahead and draw the next few frames of video on your video display device or your monitor. And so absolutely, it introduces the issue of coordination. Who waits for whom and when can you operate, especially when these different devices, the CPU and all of the I/O devices, need to interact with one another together for some application. And so here we have the same scenario, and let's now draw in the device controller. You have a device controller for each of your input devices, be that the microphone, the video camera, or your keyboard for the singing and the live streaming performance, as well as the document editing applications. And then you also have I/O controllers for each one of your output devices, for your speaker system, for your video monitor, as well as for your printer, perhaps. And so inside of each device controller, let's consider what components at a high level, what we have. And so each device controller has a local buffer. And the job of that buffer is to store data. And that data can come in two directions. It can come inbound from the device. And so in that case, when that data comes inbound to that buffer from the device, it's the device sourcing that data so that the CPU can ultimately take that data and shuffle it into memory across the system bus. And so in the outbound direction, you have data stored in this buffer. And for the outbound direction, when you store data in the device controller buffer space, that data is being staged because it's going to be sent to that device itself. So in the case, for example, of the speaker system, when we have data in the local buffer for the device controller for the speaker system, that data is being staged such that you can ultimately will be sent to the speakers in the form of sound. So you're going to actually oscillate those speaker cones and actually produce sound from that. And so these buffers can take data and they can give data depending on the particular device. And there are some devices where it can be two-way, right? So you can imagine for some touch-sensitive devices, if you had a touch-sensitive screen, you could have a device controller with an associated buffer, and that buffer, when you're reading the touch gestures on the touch screen, it's sending data from the device to the I/O device controller buffer, and then when you are sending data to the screen, you're taking data from outside across the bus to this I/O buffer and sending it to the device. So you can have data inbound or outbound to these buffers, but the main takeaway for this slide is that each device has a device controller, and each device controller has an associated buffer, and that buffer is used as a waiting area or staging area for data, whether that's inbound or outbound. Okay, so the CPU then moves data to and from main memory to or from these local buffers. So let's take the microphone example, right? So data comes from the microphone, is staged in the I/O controller buffer for the microphone, and then the CPU takes that, sets up the pathway between that buffer for the microphone I/O controller to random access memory. So it goes across the bus, makes its way into RAM, and now you have voice data in memory that the CPU can now operate on. So then the CPU decides it's going to play that sound that someone has input through this I/O controller for the microphone. So what does it do? It performs some computation, and then it sends this data along with a control command to the I/O controller for the speaker system, and then that speaker system then takes that data, which is the sound data, and it plays it on the speakers themselves. Okay, so the same deal with a live video streaming. You take your audio-visual data from the I/O buffer for the I/O controller for the video camera. You pull that into RAM, the CPU does, and then it sends it out to the buffer for the I/O controller for the video monitor, and then that video monitor gets that data from its buffer to then display the video frames that you see at audio-visual performance. Likewise with your word processor, that data comes from the I/O buffer, maybe from your keyboard, and then that's pulled into RAM, those keystrokes. It's analyzed, and then when you want to go print something, it's taken from RAM, from memory, sent to the device controller buffer associated with the printer, and that I/O controller, device controller for the printer, knows how to control the read-write heads and the print elements and spit out bits of toner in the right place on the paper, and you get a printed document. So you have all of these systems, these I/O controllers, acting as these intermediaries, and on the device side, they expose a controller, but they also have a buffer space available, and that's used for inbound or outbound data purposes. So each I/O device and CPU can execute concurrently, and each device controller is in charge of a particular device type. So you have printer device controllers that know how to talk to printers. You have network cards that know how to talk over Ethernet. You have audio controllers that know how to talk to audio devices. And each device controller has its own local buffer that it uses to store data. Now the CPU then moves data to and from main memory or to and from this local buffer. So the CPU stages data that's outbound by sending it to the buffer, or it can receive data that's inbound by reading it across the bus from this local buffer for each of the I/O controllers. And so I/O is from the device to a local buffer of the controller. And it's that buffer that is that pool storage that contains that data. You never get the data directly from the underlying device itself. And so what happens then? When data is available in this buffer to be used by the CPU, or for the CPU to send it to the buffer, the device controller on the inbound side, it informs the CPU that it's finished some operation. And what is it called? It's called an interrupt. So for example, let's say your network card, you're getting data across the network and you don't yet have any network data, right? You don't yet have any video data for that live stream. So all of a sudden, a bunch of video frames come in and it's now available and loaded into the I/O controller for the network card, those buffers, by the network subsystem. So now that data is ready to be displayed. How does it let the CPU know if the CPU is operating concurrently? It has to tell it. And that notification is called an interrupt. And it's called an interrupt because it literally interrupts the CPU and says, oh, wait a minute, taps it on the shoulder, so to speak, and says, oh, I know you're working on something right now, but I have some data available. So the CPU pauses what it's doing, switches to the loading or the servicing of that data from the buffer of the I/O controller, and then once it's done, it resumes. The CPU resumes what it was doing before it got that notification. Okay, and so these so-called interrupts are very common, and an operating system is known as what's called interrupt-driven. It's just waiting, waiting, waiting for something to happen. The interrupt is responsible for transferring control to something called the interrupt service routine. And what that service routine's responsibility is it implements the what do I do. For example, you have a buffer in an I/O controller for the network card. You have a buffer full of network information. What do you do with this data? Well, that's handled by the interrupt service routine. The interrupt service routine for that network data, what does it do? It goes to the right place associated with the network card. It triggers the bulk data transfer of that network card data. It puts it in a memory buffer in main memory. And so that ISR is the workhorse that implements all of the behaviors that have to happen in order to interact with the data buffer for each one of those I/O controllers. And so it's through the interrupt vector that contains the addresses of all the so-called service routines. And this interrupt vector is just a list of all the routines that know how to interact with the local buffers associated with each one of the I/O devices. And so what does this interrupt system need to do? Well, the architecture has to save off the address of the interrupted instruction because the CPU is merely working on something before it receives an interrupt. And so there are two types of interrupts. One is called a trap and the other is called an exception. These are both software-generated interrupts that can either be caused by an error or a user request. So what does this mean? There's one type of error that occurs when one program in memory tries to overwrite another program, right? These traps are thrown to notify to the system, the CPU, the operating system in general, that somebody has done something offending, right? It takes the CPU, interrupts it, and then goes ahead, calls the service routine that then handles that particular issue. And so if you violate your memory space limitations or boundaries, what happens? Well, the service routine, it kicks that program out of memory. An exception is caused by a user, rather an exception deals with errors. I'll correct that. An exception deals with errors, but a trap is triggered by a user request. So the operating system makes available certain libraries that are very useful routines that allow you to do things like copy files from a disk into memory. That's a file read. And so what happens, it makes available to your programs an API call, the function call. When your program executes this function call, it triggers a type of interrupt. And what that interrupt does, it then goes to your I/O controller for your disk, and it says, hey, here's a command that's used to read stuff from the disk. So it presents this command to the I/O controller. The I/O controller, under the covers, goes ahead, interacts with the device. It grabs data off the disk, puts it in the local buffer for the disk controller, and then it returns back to the CPU, triggering it saying, hey, I have data. Okay, and so that's one example of a service routine, and that's one example in particular of a trap. And a trap is a mechanism that's used to interrupt the CPU whenever somebody calls a routine that requires interacting with some kind of device. And so an operating system is often characterized as being so-called interrupt-driven because the operating system just sits there and waits for these interrupts to occur. And interrupts are used to drive all sorts of things, from scheduling processes to interacting with devices, as well as flagging errors and making sure that programs don't do things that are offending to the policies put in place to keep programs from stepping all over one another. Okay, so let's take a look at a general schematic about what an interrupt service routine might look like. Okay, let me go back and let me set my pen color. I'm going to set it to black. So here we have our CPU, and we have our bus, and we have random access memory, RAM, our main memory. So in main memory, let's say, and I'm going to draw that really large because I want to store stuff in memory, and there's a bidirectional connection between each one of these devices and the bus. So the CPU has a bidirectional connection, RAM has a bidirectional connection, and let's also imagine that we have a disk, right? So I'm going to draw the disk over here, bidirectional, and this disk I'm going to draw as a drum here, as a cylinder. Okay, so this is your disk down here. Okay, so now what happens? Well, the CPU is running, and inside RAM, we have a special place in RAM called your interrupt vector. Interrupt vector. And this interrupt vector has a number of memory locations or addresses, and these addresses are going to store the location of a bunch of programs. So here's program number 1. Here's another program, number 2. And so each of these programs we're going to call an interrupt service routine. The first program knows how to interact with the disk, and let's say the second program, it knows how to interact with your wireless antenna. So let's just imagine that's our wireless antenna for wireless communication. So now what happens? Let's say your CPU is running and you run a command using a command library called read file. Well, that read file routine, when it's called, the CPU is executing an instruction, it issues what's called a trap. And what that trap does is says, okay, I'm going to stop my execution, and I'm going to remember somewhere the address in a program that I'm executing. So this address, so this is where I left off, address in your program. So then what it does, it says, okay, I'm going to remember where I left off. I'm going to write that down so it knows where to start resuming its execution when that interrupt is triggered by this read file. And then it says, okay, this read file corresponds to operation number 1. So it says, okay, well, I'm going to go here and look up operation number 1, the first entry in this table. So it says, the first entry in this table refers to program 1, so I'm going to execute program 1 line by line. When it executes program 1, reading out of memory, line by line, this program implements everything that CPU needs to know in order to set up the transfer of some piece of data from disk across the bus and into RAM. And now you have your file that used to be on disk only, a copy of that file, so I'm going to say file, is now in RAM. And so once that file copy is done, this program finishes, and the interrupt system says, okay, where did I leave off? Let me read that leave off number, and now I'm going to resume that location, reading out instructions in RAM where I should continue executing. Now, all of that happens underneath the covers, but to you, in something like a programming language like Python or C, you'll say something like file identifier equals read file, and you give it the file name. Maybe it's a text file, .txt, right? So you do that, and all you get is a return value with a file descriptor, and now you just say string A equals read using that file identifier. Now, of course, underneath the covers, when you say read the file, Now, once that read file returns, that file is now in memory. But how that file gets there in memory is because your CPU issues a trap and it switches execution by lookup to the first operation, and each thing like a read file, write file, read the disk, read the network, so forth, is associated with a different routine, different entry in this interrupt vector. And each entry corresponds to the address or location of a different program, and this set of programs are called your interrupt service routines. And these are just programs that implement what should be done when a particular interrupt occurs. And for things like disks and printers and network cards, they implement how to access data and give commands for each one of the I/O controllers associated with the various devices on your system. Okay, so let's continue. And the operating system, because of this interrupt handling, because it saves off this address where it left off, it preserves the state of the CPU by storing certain information. Now, I talked about this address where it left off, but that's not the only thing that it stores. It also stores the intermediate values that it had before that interrupt was thrown, that trap occurred. And it also saves what's called the program counter. The program counter is literally that particular location in the program where you left off. And we'll talk more about that in detail. And so what this handling does, it determines what type of interrupt has occurred. And this is done by two different methods. I explained to you a vectored interrupt system where you have a table entry for each of the different types of interrupts. And there's also a polling method where you're actually going and checking to see, okay, well, an interrupt occurred, let me go and search through a bunch of entries that'll tell me which one actually triggered. And you might have a Boolean flag that says true or false, whether or not one particular interrupt occurred or not, a flag or status register. And there are separate segments of code that determine what action should be taken for each interrupt. Now, I've shown you this as routine. It could actually be physical routines, or it could be entries in segments of codes. So if you have all your behaviors implemented as code in one section, then you can use that particular approach. So let me draw a little schematic that demonstrates this idea of a single segment of code into which the service routine indexes. So I might have a block of code, and this is my service code. I'll call it service code. And maybe the first 5 lines represent the behaviors to take for interrupt type 1. And maybe interrupt type 2 are handled by the next 7 lines of code. And then maybe interrupt type 3 is handled by the next 3 lines of code. So in that particular case, when you get an interrupt, instead of a different interrupt pointer to a function, what you're getting is an offset. So if you have interrupt type 1, it's going to be an offset of 0. If you have interrupt type 2, it's going to be an offset of 5, because that's 0th offset. This is the 5th offset. So that's 0, 1, 2, 3, 4, 5. And that's 6, 7, 8, 9. This offset is going to be 11, 8, 9, 10, 11. And so in this case, this segment-based approach, you can have separate interrupt service routines, like we talked about before, program 1, a separate program 2, and you have a table that lists pointers to each one of these programs. That's an interrupt vector, or this interrupt vector can be implemented as a set of offsets. So you're saying offset 0, offset 5, offset 11, for example. Okay? All right. So let's continue. When your interrupt fires, you have different statuses that the CPU and the I/O device can engage in. So your I/O device, recall, as we said, it can operate concurrently with the CPU. And so here we have your CPU. It's running a user program. Let me pick up my pen again. Let's do red this time. When this signal for the CPU is high, that's when you're running the user program. When this signal goes low, that's when you're processing the interrupt. That means it saves away at this juncture, saves the current program information. So it saves off information for the current executing program. So then when it comes down here, that's when it's doing the interrupt processing. So before you can process the interrupt, call the service routine, whether it's the vector-based approach or the offset-based approach, you have to save off the current program information because you're going to be switching execution from the user program to the interrupt service routine program. Okay, so here we have the I/O device, and initially the I/O device is sitting idle, right? It's not doing anything. And then all of a sudden, an I/O request happens. Someone asks the I/O device to do something. Maybe it's a network card, incoming data arrives. Maybe it's a microphone, you start talking into the microphone. So you get this I/O request, and once the I/O request comes in, all of a sudden, you come down here, and it's no longer idle. It's now transferring I/O into some buffer. Okay. So that transferring, it happens, takes some amount of time to happen. And while it's happening, the CPU is merrily running that user program in time, where time increases going to the right. So then the transfer is done, and after the transfer is done into the I/O buffer, now that I/O device is idle. The disk stops spinning. The network card is no longer taking data across the network, and it's in the buffer. So then once that buffer is full on the I/O device, the device controller, it then triggers an interrupt. It's telling, hey, CPU, there is data waiting for you. You need to stop what you're doing and transfer this to RAM. Okay, so this interrupt is signaled. When the interrupt is signaled at this point in time, that's the interrupt signal. The CPU saves away the current program information that is currently executing and goes into the interrupt processing stage. So that's where it calls the service routine, and that service routine then copies that information waiting in the buffer associated with the device controller. That takes time to copy into RAM, set up that pathway, and trigger that copy. And then it's done copying. So what happens? The interrupt is fully handled, and then the CPU restores current program information, restore current program information. And after it restores it, it continues executing that program. And now, at this juncture, you have the information from the buffer for the I/O device is now in RAM and ready to be operated on by that program. Okay, so this cycle repeats again and again and again. And it's really important to remember the coordination that happens between the CPU and the interrupt service program. Okay, so the I/O can be of various sorts. It can be blocking. And what blocking means, that in the program that's executing, when the I/O call happens, that CPU doesn't do anything until the I/O operation is complete. So you have what's called a wait instruction, idles the CPU. You have a wait loop, and once that I/O operation is done, that's when control returns. Okay, so that means at most one I/O request is in progress or outstanding at any given time. You can't have simultaneous I/O requests. The other type of I/O request, non-blocking or asynchronous, it triggers the I/O request with that I/O device. And immediately after triggering or signaling that I/O request, the return or control comes back to the user program and it continues operating, and it doesn't wait for I/O completion. And what happens there is once that I/O has completed, it says disk start reading. Once you're done reading, the disk then asynchronously triggers or signals with an interrupt to the user program, hey, I'm done now. It's like interrupt-driven programming. And so this is done by a system call. And this non-blocking or asynchronous I/O is done through a system call that requests the OS to allow the user to wait for completion. And so you have a system call that implements this, and you have typically a device status table and asynchronous I/O, and it checks the status table, constantly polling to see if this I/O device has completed its operation. And once it has, it then notifies the waiting program. So the operating system in the non-blocking case, it indexes into the I/O device table to determine the device status and then modifies that table entry to include the interrupt. And this asynchronous I/O, the system call is typically called a select. You're querying the device status table to see if that device is done. Okay. Our discussion about buffer space and movement of data from buffer space to memory motivates a discussion on storage in general. Before we do that, we'll begin with some definitions and notations and a little bit of a review. So the basic unit of computer storage is the bit, and the bit is either a 0 or 1. It's a number in base 2. The reason for that is because a logic 1 is represented as 5 volts, and a logic 0 is represented as 0 volts. And therefore, because the state of electricity in circuitry is used to represent data, we use base 2 because it's most easily represented as binary. And so 1 bit is the basic unit of storage. 8 many bits are collected into a unit called a byte. 8 bits make a byte. A word is the native unit of storage for a computer. So when you talk about a 64-bit architecture, that means the native storage is chunks of 64 bits. So you have 64-bit registers. 8 times 8 is 64. So that's 8 bytes is 1 word in a 64-bit architecture. Okay, so in computer storage, there are lots of other units of storage that are often discussed, and we'll just highlight some of them. So a kilobyte, or 2 to the 10 power, is 1024 bytes, right? Notice it's kilobyte with a big B and not kilobit with a little b. So a kilobyte is 1024 bytes. A megabyte, or 1 meg, is 1024 squared, or 2 to the 20 power bytes. A gigabyte is 1024 cubed bytes. So when you talk about a 500 gigabyte hard drive, that's 500 of these 10 to 24 cubed bytes. A terabyte is 1024 to the 4 bytes. And then lastly, a petabyte, or PB, is 1024 to the 5 bytes, where 1024 is 2 to the 10. So we have 2 to the 10, we have 2 to the 20, 2 to the 30, 2 to the 40, and 2 to the 50 power. A petabyte is a lot of storage. So computer manufacturers often round these numbers off and say a megabyte is 1 million instead of 10 to the 24 squared, right? So just please know that when you buy a gigabyte hard drive or gigabyte memory stick, that's 10 to 24 to the 3, but just to make it easier to the casual consumer, they often round that to base 10 number and not using the correct base 2. Okay, so let's talk about the storage structure. And main memory is the only large storage media that the CPU accesses directly. So it talks over the bus, sending data to main memory, random access memory, or RAM, and it retrieves data, either that information or actual pieces of programs from main memory. And so this is done random access, meaning that it doesn't have to be done in any particular order. And this memory is volatile. And volatile means that when you turn off the power, all of the information stored inside of this memory goes away, right? So you cycle off the power, everything that was in main memory goes away. So let's take a little bit of an illustration, or make an illustration for the relationship between the CPU and your main memory. So I'm going to select black for this one. So we have our typical von Neumann computer architecture, and we have here one box. Eventually, I'll get used to using this tablet again. That's the CPU, Central Processing Unit. It is connected bidirectionally to that high-speed substrate, the bus. And then we have main memory here. And typically, that's random access memory. Okay, so we have our main memory. And just for the sake of discussion, each main memory location stores a byte, 8 bits, and each one of these 8 bits has a number called its address. That's how you identify each of these memory locations. So this is the 0th bit byte, this is the first byte, this is the second byte, this is the third byte, fourth byte, and so forth. Each one of these bytes is 8 bits. Okay, my drawing isn't very good. But nonetheless, we have main memory, and stored in main memory, we have maybe programs, and these programs have instructions. These instructions are read piece by piece by piece, one word size at a time, or multiple word size sometimes. We also have data that's sitting in memory. Now, of course, when the CPU is going to execute an instruction, the CPU consists of a number of different elements. There's the arithmetic logic unit, or ALU, that does arithmetic instructions. There's the floating point unit, or FPU, that does decimal types of operations. There's something called the instruction cache. That's what's used to store pieces of program instructions. And there's also something called the data cache, which stores pieces of data on the CPU. You also have something called your register file. Here's your register file. And the register file has temporary storage, one word at a time, and that's used to hold temporary values. And then we also have something called the program counter, and the program counter is used to store a memory address, and it's the memory address of the next executable instruction. So initially, the program counter is going to have an address that refers to or points to a particular instruction in the program. So what happens, the CPU fetches a piece of the program, it grabs it across the bus, and puts it in the instruction cache. And then one instruction at a time is read out of the instruction cache and used to modify the ALU, as the floating point unit, to implement whatever that instruction might mean. So then the next instruction is fetched, and the next instruction is fetched, and the next instruction is fetched. And so when we access things from main memory by the CPU, this doesn't have to be in a sequence. It can be some arbitrary location. So in one instant, it could be from this area of the program. In another instant, it could be accessing some piece of data, and then another part of the program, and so forth. If you cycle off the power, everything in main memory goes away, and you have to rerun this program from scratch. That means it's volatile. So we also have another type of storage, and this is called secondary storage. And the secondary storage is treated as an extension of main memory. And what do I mean by that? So let's take a look at one type of secondary storage, namely your hard drive, your disk. Now, your hard drive or disk is a little bit different because it preserves data if you turn off the power. Moreover, this disk has much more space, storage space, than main memory, but the problem is this disk is a lot slower than main memory. And so typically, when you think of memory, you think of it as a hierarchy, a set of interacting types of memory, where the trade-off is slower and bigger versus smaller and faster, more nimble. Okay, so one of the interesting pictures, this picture, I thought I'd include that, is MS-DOS. And MS-DOS was the big Microsoft operating environment. And what happened in MS-DOS, when you ran a program, that program literally took over or took control of all of memory. And later, MS-DOS became Microsoft Windows, which ran on top of DOS, and it provided a graphical look and feel on top of MS-DOS, but it still wasn't a true operating system in terms of sharing at the same time all of the resources of the underlying system among the many applications. And so one of the things you'll notice in this version of Windows, this is Windows 1.0, is that you didn't have overlapping windows. It's gotten a lot more sophisticated over the years, but it's very simple, and its whole purpose was to provide a nice, friendly graphical shell on top of MS-DOS, which is down below, which is strictly on the command line. And so the memory hierarchy at the time was very simple. You had main memory, and you also had some floppy disks, removable disks, that weren't very high density storage, but they were much more than the available main memory at the time. So let's take a look at these disks. These disks are called disks because if you were to open up these devices, they have a rigid metal glass or plate, and it's covered with magnetic material. And it just so happens the axis of magnetization is oriented differently, and it can be energized or de-energized to encode a 0-bit or a 1-bit. So over here in this picture on the left, the lower left, we have a picture, and I'll use red, of an actual hard drive. Someone's opened it up. And so these are the platters. They almost look like rectors, and these things will spin in some direction. And then this is called the read-write head, read-write head, and it has on the end of it a little electromagnet, and that electromagnet can either read the magnetic field in each part of this disk as it's spinning, or energize it differently to change an area from a 1-bit to a 0-bit or 0-bit to a 1-bit. Now here we have a bunch of parallel magnetic disks. Here's the first disk. Below it we have the second disk platter. We have the third disk platter. And this read-write head, it moves, right? It turns this way. And when it turns either this way or the other way, it actually positions this read-write head along different parts called tracks of this disk. And so if we look at a logical decomposition of what this disk looks like, here we have a single platter. It's typical, and this read-write head has a different head for each of the platters. So there's one on the first platter, there's one over the second platter, and there's one over the third platter. And it'll literally lower this read-write head close enough that it can impact with the electromagnet. It can change the magnetic state of that magnetized material on the disk platter. So in this logical construct, this map, if you will, we show what the disk, how the disk is logically organized. And so each ring, if you will, they're concentric rings, is called a track. So that's track 0, track 1, track 2, track 3, and they're numbered, and so forth. And then each track has what's called a sector, right? So that might be track 0, this first 0 sector, track 0, the first sector, track 0, the third sector, and so forth. So every single region, track, and sector can store a few bytes of information. And so when the read-write head writes, it needs to know the address on the disk, i.e. which track, which sector, also which platter. This is the first platter, this is the second platter, this is the third platter, which track, which sector, and which platter it's going to write to or read from. And so this read-write head, what will happen is this platter will start spinning like a record, and then this read-write head will seek or move to the right track, and then it'll position it downward to get the correct sector as it's spinning by. And it all happens very quickly. And so this disk surface is logically divided into tracks and sectors. But if you take each of the tracks and sectors and you organize them, going from the 0th track to going all the way around along all the sectors in the 0th track, do the same thing for the next track, the same thing for the next track. All of the bytes arranged around those tracks and sectors, if you concatenate them, well, to the read-write head, it's logically organized as if it were just one single tape. Now, these are the individual tracks and sectors for each one of the tracks, going from the first track to the second track to the third track, down to the next platter, down to the next platter, down to the next platter. You line them all up, and logically, what it looks like is just one long continuous tape that has bytes of data along it. So while it looks logically, and this is logical organization, like a single tape containing information, the physical arrangement, physical, is a set of sectors that are lined along certain tracks, and it's in an orderly numbered fashion. And so the disk controller, one of the jobs it has, when I talked about the controller is responsible for interacting with the device itself, it hides those details, but the disk controller in particular determines this logical interaction between the tracks and sectors, i.e. the device, and the computer. Okay. So many of you are more familiar with solid-state disks, and solid-state disks are basically no disk at all. It's really just a set of chips that give you random access to storage, and it's effectively speeds like you have for main memory, like RAM, but it's not volatile. They've worked out a way to preserve all the information when you turn off the power. And so these take a lot less heat. They're more durable because you don't have moving parts. Over time, this magnetic surface, it degrades, right? But just from usage. And because it also has mechanical parts over time, things that move eventually break. Okay, so these solid-state disks, or SSDs, are much faster, and they're non-volatile, just like the regular hard drives, the disks. And they're becoming much more popular. They're faster, and they're more energy efficient, but they're a lot more expensive. You have to pay money for all this engineering that goes into them. Plus, these are more expensive. The actual physical chips and devices that go into making these is much more expensive. So while solid-state disks are faster, they are much more expensive, and you tend to get much larger storage volume with traditional disks than you can with SSDs, at least for reasonable amounts of prices. So right now, you can typically get a 500 gigabyte SSD for not too much money. You can get a 1 terabyte SSD for about maybe, let's say, $100 or so. And then if you go to 2 terabyte SSD, that'll run you about $220 to $250. And then if you go to 4 terabyte SSD, that'll usually run you maybe about, these days, about $500 or so. Now you can go higher than that, but it gets really expensive really, really fast. Whereas if you get a 4 terabyte hard drive that just has the traditional disk platters, that'll run you probably about $150 to $200 for a very high quality one. So it's much, much cheaper to get a hard drive. Okay, there's also, you'll see something called an SSHD, right? That stands for solid state. That's the SS, solid state. Hybrid drive. The HD stands for hybrid drive. And what that does, it has the SSD component. So it has all of these chips that implement very fast, high-speed memory. And remember, it's expensive, but it also has attached to it, it has those platters for the regular hard drive. Here's the HD. And so what this device, this SSHD does, SSHD, it says, okay, I'm going to present a controller, and that controller is going to take data from the hard drive, but what it's going to do is put that data off the spinning platters, large chunks of it, in the solid state storage. Now, this is slower, this HD is slower, but once you put a big chunk of data in the solid state portion, now every time you access that big chunk of data, you're going to take it from the solid state portion. Now that's very fast when you access it from the solid state portion. And the idea is that if you're working with a piece of data, you usually work with it in chunks anyways. And so the hit to performance that you take is you load it once, you work with it many times, quickly. And then when you need the next region of data, you load that again. And so in terms of slow on the scale to fast, you have hard drives as being relatively slow. You have SSDs, solid state drives, as being fast. And then you have solid state hybrid drives in the middle. And of course, a solid state hybrid drive where the solid state portion is small is going to tend to be slower. And SSHD, where the solid state portion is a lot bigger, is going to be faster. Because the bigger this solid state portion in the hybrid drive, the faster it's going to be, because you're putting bigger chunks of data from your slow storage device into the fast storage device and then accessing it. Now, this idea of a solid-state hybrid drive is an instance of caching, and that's going to be a subject we'll actually devote a little bit of time to in this class. And so this idea posed by the solid-state hybrid drive is an instance of a so-called storage hierarchy. Storage systems are organized in a hierarchy in terms of speed, cost, and volatility. And in similar fashion, we had our access for the SSHD coming out of the solid state portion. But when we had this larger but slower storage space, the hard drive portion, that we used to fetch that data. And so this organizing of data approach or data types that interact with one another to give you speed improvements, but give you the benefits of high amount of storage is called caching. And the storage hierarchy is how you arrange these different types of interacting memories. And so what caching is formally defined as is the copying of information into the faster storage system in order to get performance improvement. And so if we think about it, main memory in a von Neumann architecture acts like a caching system for secondary storage. So remember, in your von Neumann architecture, you have your bus, and you have your main memory, and this main memory is fast and it's random access. We also have our disk, our secondary storage, and this is our hard drive, okay, our hard drive, and it has the platters and all that good stuff. And so you can think of main memory as being a kind of cache for the hard drive. So why is that true? Let's say you're watching a video. This video exists in its entirety on your hard drive, and that video is chopped up into pieces, and then each piece is brought into memory, and when you go to watch the video, the CPU fetches this video and pushes it to your graphics display, to your display device. It does that, fetches it from main memory. So this access is fast, so it pulls it out, sends it to your I/O controller, does some processing, sends it out, and you see your video. So you do it for the first piece of the video, the second piece of the video, third piece of the video, and then when you get to that last piece, what do? You load the next chunk of the video into main memory, and you continue fetching from that next chunk. So in essence, main memory acts as a cache. It's much faster than the hard drive, which is much slower. And just by interacting with them, using the main memory to store a subset of that data from that slower hard drive, you can get a performance improvement. And so caching is this approach of copying information to a faster storage system such that you realize a performance improvement. And so the device driver for each device controller, when it manages the input-output, we talked about this idea of the device side versus the interface side. So suppose we have our system bus again. Here's our bus. And let's assume our bus connects to a disk controller. This disk controller knows how to spin the platters of the disk to get them spinning, move the read-write head, and so forth, right? Knows how to do all of that. We also have this quantity called a device driver. Now, this device driver is a piece of low-level software. It has low-level software. It's running in main memory. And this device driver knows how to interact with this disk controller. And maybe this disk controller has a command control buffer. And when you put a certain pattern of ones and zeros in there, it represents a different command. It knows how to interact with the disk controller in order to fetch data. And what this device driver does, it provides a clean interface that you use when you're trying to interact with the disk controller and ultimately with the disk itself. And so this device driver is how the operating system kernel interacts with these devices. So here we have memory, main memory. We have our kernel, our operating system kernel, and that operating system kernel uses device drivers, device driver, to interact with the controller in order to realize, here's the controller, the behaviors in a clean way. Because this device driver will have standard interfaces for how you write data through the interface controller to the device and how you read data from the controller to ultimately from the device. And the reason why we have this device driver is because this interface stays the same, right? So it could have a function called read that returns data. It could have a function called write that sends data. So read and write stay the same, but you can change the device driver if the implementation details change for the controller or for the hardware itself. And so now, as long as your kernel is written to make use of these well-known interfaces or commands, read and write, you can change the device driver implementation if you get a new device, but the kernel stays the same. And so the device driver's purpose is to provide a uniform interface to the kernel to interact with the controller for that particular I/O device. Okay. So here's a nice picture. This is from the book, a picture of storage hierarchy. At the top here, we have volatile storage. And volatile storage is that storage for which when you cycle off the power, all of that information disappears. We have the registers that are inside of the CPU, the register file. We have the cache. These are the instruction cache and the data cache on the CPU. We have main memory. This is random access memory, RAM, as you might know it. And then below this dotted line, we have non-volatile storage. We have non-volatile memory, like programmable, like SSDs and things like that. We have hard disk drives, have optical disks, like DVDs, CD-ROMs. We even have magnetic tapes. And you might think, gosh, well, who uses magnetic tapes? They're used for high bulk data storage. We're talking terabytes of data storage. And so as you go up in this hierarchy, non-volatile, it gets smaller and smaller and smaller, the capacity, but the access time gets faster and faster and faster. So the fastest storage that you can have is inside the CPU, namely the registers. And these registers are typically used for intermediate values. So when you have a computation that says something like A equals B plus C, when you do the adding of B plus C, that result has to go somewhere before you assign it to A. Where does it go? It goes into the registers until it can actually assign it to A. And all assigned to A means is that there's a memory location. Here's your memory, and it's referred to by this name A. And when you assign to it, you're really writing in that value B plus C. So if B is 1 and C is 2, you're just writing in A, that value 3, but that 3 is temporarily stored here before you do the assignment into main memory indirectly through the bus. Okay, so the registers are the fastest in main memory. It's non-volatile. It's a lot slower, or a little bit slower than registers, but it's still a lot faster than things like your hard drive. Now, as you go down in the hierarchy, it's non-volatile, so you cycle off the power, that data persists, but the amount of storage gets bigger and bigger and bigger. Okay, so it's really important to understand the interaction between these different types of memory. So I encourage you to pay special attention to that when you're reading through the textbook. Okay, so what is caching? Caching is an important principle and it's performed at many different levels in the computer. It's done in hardware, done in operating system. It's even done across machines and servers. And information in use is copied, typically, from a slower storage temporarily to faster storage. And this faster storage is called a cache. And this is what's first consulted to determine if the information is there. If the information is there, it's used directly from that fast memory. If it's not, then a request is made to pull in more data from the slower memory into the faster memory. And so typically what happens, this faster memory is usually smaller than the larger, slower memory. And the management of this cache to make sure you always have current information that's pulled in is really important design problem. And so you typically look at the cache size, the amount of small memory, and what policy you're going to use to make these replacements when you need more data to fetch. So here's an example of caching, and I'm going to draw down the center a line to separate the two sides, and I'm going to talk about caching as it pertains to the CPU and as it pertains to servers. So here's my CPU, central processing unit, and that central processing unit, I'm going to draw it really big here, and I'm only going to draw the CPU, and I'm going to draw main memory. Now, main memory, we said, it's volatile, and it's larger than the amount of storage that's on the CPU. So we have these two interconnected by the bus, high-speed bus, and we said the CPU consists of an arithmetic logic unit, ALU, that does logical operations. So let me define that component or subsystem of the CPU. It has a floating point unit, FPU, which does decimal floating point types of operations, things like division, exponentiation, and so forth. And then we also have the register file. That's for temporary values. It's very, very fast, but it's very, very small. And then we also have here something called the instruction cache. I'm going to just abbreviate it, IC. We also have something called the data cache, DC. I'm going to abbreviate it. So what happens here, when you run a program on the CPU, here's your program, and that program exists in memory, and that program consists of a set of instructions that are understood by the CPU. So this program exists as a set of blocks in main memory, and then you also have data that the program might use, and that data could be an image, it could be a table, what have you, and that data also exists as a series of blocks of data in main memory. So what happens, you have this other register in the CPU called the program counter, PC, and that program counter has a memory location in the beginning. That memory location is the memory location of the next instruction of the program you're going to execute. Now, in the beginning, this program counter is going to point to that first location of the program in memory. So what happens? The CPU doesn't just read one instruction, right? That would be this one little block. It reads an entire block of that program. And it takes that entire block and it moves it into the instruction cache. So here's that first piece of the program. It's in the instruction cache. So now, instead of paying the cost of reading things across the bus, where it's a little bit of a slowdown to access memory as well as to send that data or that instruction for the program across the bus, it's going to pull in a big block one time into the instruction cache, and now it starts reading those instructions one at a time out of the instruction cache. So then what happens when it runs out for that block? It says, I've run out for that block. Let me go ahead and fetch the next block of my program, and I'm going to pull that in across through the bus, and I'm going to store that other block in my instruction cache, and now I start reading. So this instruction cache, the access is very, very fast. This main memory, it's slower than the small storage space that's on the CPU, and this CPU is pulling chunks of information from main memory. Likewise, main memory can be used as a cache of things on disk. That same program that we're reading, well, that program ultimately started out being stored on disk. So let's say that program was huge. Maybe it was Microsoft Word or something like that. That program was absolutely huge. Now, of course, you can't fit all of that program in memory. So what did it do? It took that program, chopped it up into pieces, and each piece it loaded into memory. So what you see in memory as your program is just a piece of Microsoft Word. Maybe it's that piece that does the spell check when you need it. Maybe it's that piece that's doing the drawing of a figure when you need it, and so forth. So that piece of a program is pulled into main memory from disk, and then when you run out of program, what do? You pull in the next piece of the program into memory, right? And you load that, and now the CPU starts reading from blocks of that next piece of the program in memory. Now, in that case, memory is much faster than your hard drive, and your memory is a cache that's used to work faster on pieces of that larger data that's in the slower hard drive. So that's CPU caching, an example. Let's look at server caching. So you're on your machine here. That's your host, your machine. And let's say you are attached to a router, right? And you want to access some piece of information. Maybe you're at DSU or you're at your home and you want to go over the internet, maybe to access some Netflix data. And so here's the internet. And you have a data center here. And that data center is for Netflix. And you're streaming video, right? That video is being loaded across, makes its way across the internet to your host, to your browser, and you see that movie that you enjoy. There's my artwork. Okay. So now what happens is each time you want to watch a different movie, so let's say you're on campus and movies that are very popular, you're not going to be the only one watching it. Maybe somebody down your hall is watching that same blockbuster movie, right? So movies are very popular. More than one person is going to want to see that movie. So maybe there's the next person that's also watching that popular movie. And maybe there's another person that's also watching that movie. And maybe there's yet another and another and another and another person in the dorms that's watching that movie. Now, of course, DSU's population is, when it's full population, 100%, is 5,000 people. So that's going to be a lot of people potentially that are watching the same movie. And each time you want to watch a movie, you issue the fetch call, and all of those bytes for the movie have to make their way back across the internet to you. Well, one of the practical issues is there's only so much bandwidth available between DSU and the internet, and you can easily saturate that link. Well, one solution for that is on the same network to install what's called a Netflix cache. And what that cache does is whenever you issue a request for a movie, instead of downloading it and streaming it to you, it downloads it. Your request goes to the Netflix cache. So instead of going out to the internet, let me change the pen color to illustrate that. I'm going to change it to blue. Let me do that. Exit. Let me pick my pen color to be blue. So with a cache, instead of your request going directly across the internet to Netflix, your request goes to the cache. And then what happens when your request goes to the cache, it asks the question, do you have that movie? And there are two answers, either a yes or a no. If it's a yes, well, it checks its database to see if it has that movie. And if it's a yes, it loads it into memory and sends it across to you. That's the yes answer. If it's a no, it goes across the internet, the cache does, goes to Netflix, requests that movie, downloads it, and then gives you a copy. So why is that beneficial? In the first case, each person, let's say 100 people request the same movie, that's 100 of those streams coming across the wire. In the second case, the first time someone requests a movie, it's loaded into the cache server, and then every subsequent request, the second, the third, the fourth, up to and including the 100th, instead of reaching out across the internet to Netflix, saturating this access link to DSU, it's going to get it from the cache, and it's really hard to saturate your local area network because typically on campus, well, I think it's gigabit switched Ethernet, and the backbone is 10 gigabit switched. And so we have a lot more bandwidth on the local network here, including the cache, than we do going across the wide area when you go off network. And so that's server caching. And in server caching, we use the faster access locally on the same network by loading that data from the slower source across the internet to that faster source, which is local. And then we subsequently use what's from that faster storage. Okay. So Netflix actually sells and offers Netflix caches. It's called OpenConnect. And I'm not familiar with what the price is. It might be $5,000 or $10,000 a year. But if you think about it, it saves you a lot more bandwidth, and it gives you a lot faster response time, especially for popular movies, which is where caching is very beneficial. So we're going to end there. This is about direct memory access. We're going to end here. And please make sure you're keeping up on the reading and you are looking at and working on the homework. So that's all I have for today. Have a great weekend. I will see you on Tuesday. As always, please stay safe